Today we're going to talk about stars. How do they form, and what do they become when they die? Stars form when a cloud of mostly hydrogen gas in the universe begins to collapse under its own gravity. As more particles fall in, the protostar becomes denser and hotter until hydrogen particles can smash together to create helium in a process called nuclear fusion. The star will be a main sequence star until all the hydrogen in its core is used up. The heat energy created in this fusion reaction counters the force of gravity, allowing the star to resist further collapse. But when the hydrogen is used up and no more heat energy can be created, the star faces crisis. Without the heat energy holding the star up, gravity takes over and the star's core collapses. This infalling matter heats the star even more, and as the helium core collapses, the outer layers expand because of the heat energy it creates. This actually allows hydrogen to fuse in the outer star. The outer expansion reduces the surface temperature of the star, turning it from yellow to red. Thus, the star enters its first red giant phase. As the core collapses, its temperature reaches 100 million Kelvin, the temperature when helium atoms can fuse together. A flash of helium fusion creates carbon and oxygen in the core for the first time. As the helium fusion continues, the star is momentarily in equilibrium against the force of gravity again. But as before, this moment of peace does not last. As all the helium is used up in fusion, the force of gravity takes over once again. As the star becomes a red giant once again, the collapsing carbon-oxygen core sends out solar winds and UV radiation that blast off some of the outer layers of the star and create more fusion in this planetary nebula. This process can even make new elements. With its outer layers gone, the core continues to collapse and heat, but is not able to produce the high temperatures needed to fuse together the carbon or oxygen, which would produce the energy needed to hold the star up against the force of gravity. The star eventually becomes so crushed that atoms are forced together. But according to the Pauli exclusion principle, the electrons in the outside of these atoms cannot occupy the same place at the same time. So these electrons exert a force on each other that is so strong it can balance the massive amounts of gravity acting on this mass. Low-mass stars will stay in this crushed state for an indefinite amount of time, cooling slowly as they turn from white dwarfs into black dwarfs. Higher mass stars are able to produce the temperatures needed to fuse carbon, oxygen, and even heavier elements, so they will go through the process of becoming red giants many times over. But the process stops at iron. Fusing iron takes away energy rather than giving it. Unable to fuse anymore, the star begins a final collapse. However, the mass is so great that even the degenerate electron force that held up the low-mass star is overcome by gravity. Electrons are forced into the nucleus, where they combine with protons to make more neutrons. Those neutrons repel each other by a degenerate force like the electrons did, but much stronger. The core is supported now, but the final collapse sent a shock wave through the outer star, creating a spectacular phenomenon known as a supernova. The energy inside a supernova is so great that it can fuse elements heavier than iron and send them out into the universe. The core that remains is called a neutron star, and like a white dwarf, it will exist in this state indefinitely. Stars that are more massive than 3 solar masses cannot even be supported by the neutron degeneracy force. In fact, no force in the universe is known that can support such a huge amount of gravity. Instead, the nuclei crush together into an infinitely dense, infinitely small point, and the star becomes a black hole.